Hi, my name is Zirui. In this video, I'll be presenting our work on leveraging untrustworthy commands for multi-robot coordination in unpredictable environments. The robots always need to coordinate their actions with one another in the tasks such as environmental monitoring, target tracking, and visual mapping. These tasks can be very challenging because the robot actions can have information overlap and the environment can be unpredictable. Let's see how the challenges will appear in a multi-target tracking scenario. Here, we can see that this trajectory on the left will result in larger information overlap compared to the one on the right. The objective function capturing such information overlap can be modeled as a submodular function that satisfies this inequality. To overcome this challenge, the robots need to select trajectories that minimize this information overlap, which is however hard due to submodularity. Then, if the targets are highly dynamic, then their future motion can be hard to accurately predict, so it's hard for the drones to evaluate the effect of all available actions a priori. Therefore, instead of future prediction, they have to use past information. The current state of the art formulates such submodular coordination tasks in unpredictable environments as a bandit problem, where the robots don't have any information about the unpredictable future environment a priori, but after selecting and executing actions, they can observe the achieved value of FT as bandit feedback. A BSG algorithm was proposed for the current problem formulation, which can learn actions that asymptotically achieve the one-half near optimality in non-adaptive environments. However, assuming no future information can be conservative, and the robots would naturally like to make use of some side information from human experts or machine learning algorithms to improve the coordination performance. Therefore, based on the existing work, we propose a new problem formulation where the robots can directly leverage external commands. But the commands are not necessarily near optimal. The beta here is their performance bound over the operating horizon, and whether beta is better than one-half is unknown before the commands are actually executed. To this end, our goal is to enable the robots to leverage the external commands to improve coordination even without knowing whether they will be truly better. In this paper, we proposed the meta-BSG algorithm where the key module is a meta-algorithm XP3IX. At each time step, this module will decide online whether the robots should choose BSG or the commands. The intuition here is that if a strategy has recently worked better than the other, then it's more likely to be selected in the future, and vice versa. We also proved that the proposed meta-BSG algorithm is guaranteed to converge to the better strategy as the operation horizon goes to infinity. We validate meta-BSG in a 2D target tracking task where the target's future motions are predefined but unknown to the robots. It is shown that meta-BSG is able to adapt to the better strategy. Our future work will include involving external commands with time-varying performance to enable the agents to independently choose a strategy and to extend to distributed communication. Thank you.